Have you ever wondered how gold, silver, or even the iron in your blood came into existence in the cosmos? It all begins with a cosmic ballet, a dance of celestial bodies that ends in a performance so spectacular, it outshines entire galaxies, a supernova. These cataclysmic events are more than just cosmic fireworks. They're key players in the grand scheme of the universe, driving stellar evolution and creating conditions ripe for life. In the heart of a star, a process called stellar nucleosynthesis takes place. Here, under extreme pressure and temperature, lighter elements fuse together to form heavier ones, producing the diverse array of elements we see today. But the real magic happens when a star exhausts its fuel and collapses under its own gravity, culminating in a supernova explosion. This cataclysm releases a flood of energy and newly minted elements, sowing the seeds for future stars, planets, and even life itself. So, the next time you look at a piece of gold jewelry, remember its origin is nothing short of cosmic. To understand supernovae, we first need to understand the life cycles of the stars that become them. Our journey begins in the dense, cold corners of the universe where stars are born. These celestial nurseries, known as nebulae, are vast clouds of gas and dust. Here, gravity pulls matter together, forming dense pockets that eventually collapse under their own weight, triggering nuclear fusion and giving birth to a new star. This newborn star now enters the main sequence phase, the longest period in a star's life. During this time, the star's core burns hydrogen to produce helium through a process called nuclear fusion. The energy generated pushes outward, counteracting the inward pull of gravity and maintaining the star's equilibrium. As the star exhausts its hydrogen fuel, things begin to change. For stars similar to our Sun, the core contracts and the outer layers expand, transforming the star into a red giant. The core heats up, igniting helium into carbon and oxygen. Once the helium supply is depleted, the core contracts again, and the star sheds its outer layers, leaving behind a white dwarf. This stellar ember slowly cools and fades over billions of years. However, for stars with a mass about 8 times that of our Sun, the story is different. These stars become red supergiants, and their cores reach such high temperatures that higher elements like iron can be formed. But iron doesn't release energy when fused. Consequently, fusion stops, and without the outward pressure to counteract gravity, the core collapses, resulting in a cataclysmic supernova explosion. What remains after the supernova depends on the original star's mass. A core collapse may leave behind a dense neutron star, or in the case of the most massive stars, a black hole. Thus, in the grand theater of the universe, every star has its act, and for some, the final curtain call is a supernova. Not all supernovae are created equal. Indeed, these spectacular celestial fireworks come in various types, each with its unique characteristics and triggers. First, let's discuss Type Ia supernovae. These cosmic detonations don't occur in solitary massive stars but in binary star systems. One of these stars is a white dwarf, the dense remnant of a sun-like star. When the white dwarf's partner star overflows its Roche lobe, the dwarf gorges on its partner's material. Once the dwarf reaches a critical mass, about 1.4 times the mass of our Sun, it can no longer support its own weight. The result? A thermonuclear explosion that completely annihilates the white dwarf, lighting up the cosmos with a Type Ia supernova. Next, we have Type Ib and Ic supernova. These types are the result of massive stars that have shed their outer layers of hydrogen and helium, leaving behind a bare core. When these stripped nuclei meet their explosive ends, they create Type Ib or Ic supernovae. The primary difference between these two types lies in the presence or absence of helium in the star's spectrum. Finally, we have Type II supernovae, the traditional supernova poster children. These dramatic events mark the death of massive stars, those at least 8 times the mass of our Sun. When these giants exhaust their nuclear fuel, their iron cores collapse under their own immense gravity, triggering a shock wave that blasts through the star and rips it apart, resulting in a Type II supernova. It's fascinating to note that each of these supernova types is triggered by a different mechanism: a thermonuclear explosion for Type Ia, core collapse for Type Ib, Ic, and II. Each supernova type also has a distinct progenitor star, a white dwarf in a binary system for Type Ia, a bare core for Type Ib and Ic, and a massive star for Type II. Each type of supernova tells a unique story of stellar life, death, and transformation. Indeed, these cosmic fireworks are not just beautiful to behold, they are also key players in the grand tale of the universe. The death of a massive star is not a quiet affair. It's an astronomical extravaganza, a radiant, explosive eruption that outshines entire galaxies, even if only for a fleeting cosmic moment. Supernovae are the universe's ultimate fireworks display, a spectacular finale to the life of a star. When a star, approximately 8 times the mass of our sun or larger, exhausts its nuclear fuel, it can no longer support its own weight. The core collapses under the intense gravitational pressure, triggering a shockwave that ripples through the star, tearing it apart in a cataclysmic explosion. This is a core collapse supernova, an event so luminous it can briefly outshine the combined light of all stars in its host galaxy. In the aftermath of this cosmic detonation, a dense core is left behind. If the core's mass is between 1 and 3 times that of our sun, the result is a neutron star, an object so dense that a sugar cube-sized amount of its material would weigh as much as a mountain on Earth. If the core's mass exceeds 3 solar masses, the force of gravity is so strong that it forms a black hole, a region of space-time where gravity is so strong that nothing, not even light, can escape. But the spectacle doesn't end there. The explosive death of a star also leaves behind a supernova remnant, an intricate glowing shell of gas and dust. This expanding debris field is a treasure trove for astronomers, providing key insights into the physics of the explosion and the elements produced in the stellar furnace. Within these remnants, astronomers often find pulsar wind nebulae, beautiful, complex structures created by the powerful winds of energy and particles streaming from a rapidly spinning neutron star at the heart of the remnant. These pulsars are like cosmic lighthouses, sweeping their beams of radiation across the universe. From death comes new life, and in the case of supernova, the birth of some of the most exotic objects in the universe. A fitting tribute to the stars that once were, don't you think? Supernovae are not just cosmic fireworks. They play a key role in the evolution of galaxies. Now let's delve into how these cosmic powerhouses shape the dynamics of our very own Milky Way. When a supernova explodes, it doesn't do so quietly. It drives shockwaves into the surrounding interstellar medium, the space between stars filled with gas, dust, and cosmic rays. These shockwaves compress and heat the interstellar medium, creating turbulent motions that can send gas clouds collapsing under their own gravity. And when that happens, a new generation of stars is born. Thus, in a beautiful cycle of stellar life and death, the end of one star can trigger the birth of others. But supernovae do more than just ignite star formation. They also enrich the cosmos with heavy elements. You see, in the heart of a massive star, nuclear fusion processes create elements up to iron. But it's in the intense heat and pressure of a supernova explosion where elements heavier than iron, like gold and uranium, are forged. These elements are then flung out into the cosmos, seeding the interstellar medium and eventually finding their way into new stars, planets, and even life forms. Yes, that's right. The very atoms in our bodies were once part of a star that ended its life in a spectacular supernova explosion. Finally, supernovae influence the dynamics of galaxies. The energy and momentum they inject into the interstellar medium can drive galactic winds, vast outflows of gas that can escape the gravitational pull of the galaxy. These winds can shape the structure of the galaxy and even regulate its rate of star formation. In the grand scheme of cosmic evolution, every supernova leaves a lasting legacy. Each explosion is a transformative event, shaping the universe in ways we're still striving to understand. But one thing is clear. Without supernovae, the cosmos and even life as we know it would not be the same. How do we study these distant and fleeting cosmic events, you might ask? Well, the answer lies in the field of multi-wavelength astronomy. Just as a symphony uses a variety of instruments to create a rich, harmonious sound, astronomers use a range of observational techniques to study supernovae in all their complexity. Optical light curves, for instance, provide crucial insights into the initial explosion and the expanding shock wave. But the story doesn't end there. Radio waves reveal the interaction of the blast wave with the surrounding interstellar medium, while X-ray and gamma-ray observations unveil the high-energy processes at work in the aftermath of the explosion. Each of these methods gives us a different perspective, a different piece of the puzzle. Together, they allow us to unravel the mysteries of these cosmic fireworks and their impact on the galactic stage. So, even though these events may be distant and fleeting, through the lens of science we can witness the spectacular dance of the cosmos,